Thank you. So I won't make any comment on my first slide. But the talk is going to be a mixture of topology and some things about quantum computing and some idiosyncratic remarks. And so you'll have to bear with that. Since I'm trying to talk about topological quantum computing or topological quantum information, it means that I need to be able to jump back and forth between some things that are happening in topology and some things that happen in quantum computing. And so there's more than one context that's a little bit technical, and I'm interested in that mixture. And I find it sometimes a little confusing myself. So I'm talking for a little bit about knots in physics in a very general way. Lord Kelvin, Sir William Thomson, in the 19th century, had a theory of knotted atoms. And this is one of the earliest ideas of interrelating knots in physics. This was before quantum theory. And I haven't drawn a knotted atom since I don't know what one would look like. But this is from the film you saw last night, if you did, of dolphins making rings like this by appropriately shaking their heads. And Kelvin's theory was very popular. One measure of its popularity, this is just a few remarks. One measure of its popularity was the fact that people who were inspired to think about spirituality and mysticism at the time took it up. And this picture here is a picture of an atom that was drawn by the mystics Ledbetter and Besant at that time. And I was curious as to what, if anything, it looked like. And in fooling around with pictures of knots that the computer could draw for me, I found that this one is sort of close in spirit to the one that you have there. You see, it's not the same, but close in spirit. And this is given by a cosine with some frequency and another cosine with a different frequency and a shift, and then some combination of cosine and sine. It's a Fourier knot. In 3 dimensions, those are the equations for it. So it's an interesting pastime to actually try to draw knots sometimes. Then going back to general ideas about physics, this is a favorite glyph of mine due to John Wheeler, the relativist. And he draws a U for the universe. And then this is supposed to be the Big Bang over here. And it expanded. And at some point it expanded to the point and evolved to the point where it could observe itself and even see the residue from the Big Bang. So that's Wheeler's iconic glyph for the universe. But there's a paradox inherent in the glyph if you're thinking in terms of quantum mechanics, because, and according to Wheeler, he liked to say, a phenomenon is not an actual phenomenon until it is observed. Maybe he didn't say it exactly that way. A phenomenon is not actual until it is an observed phenomenon. And so then what is the actual nature of the universe before the universe evolves to the point of being able to make an observation? That's the question. Well, I would like to up-level this question a little bit because, you see, when we draw a picture of the universe, we actually, like this U, we draw that picture inside some larger space. We always do. We always back up and create yet another context in which it's all happening. And that's what knot theory is about. Knot theory is about how can one space be fitted inside another space. So I want to rewrite Wheeler's universe in this way. The knot here is meant to raise the question, and in what context is the universe existing? Which is similar and related to in what context is the observation of the universe existing. Continuing with Wheeler, in their hefty book, Gravitation, Miesner, Thorne, and Wheeler suggest that physics should be in some way a manifestation of logic, that you should think of pre-geometry, what a structure prior to geometry, something like the calculus of propositions. But maybe the calculus of propositions was not the right suggestion. Something like that, though. And so we might read logic, icon, diagrammatic categories. Topology is a kind of pre-geometry. There is actually a richness of choice for what you might think of as pre-geometry. And in fact, some of that is explored by present-day relativists who work on spin foams and other things which could be prior to space-time. In fact, one of the earlier examples of trying to do that is the spin networks of Roger Penrose, who tried to make a background to space-time out of the patterns of interactions of spinning particles, of spinning fermions. We'll see a little later on that a kind of deformed version of his spin networks is very useful for thinking about quantum computing and topology. Another piece of background here that I happen to be interested in is Witten's formulation of three-manifold invariants by using functional integrals. So for Witten, he can write down an invariant of a three-manifold by integrating over all gauge fields on the three-manifold a certain measurement that corresponds to integrating a differential form called the Chern-Simons form over the three-manifold. The A stands for a gauge field, and A wedge dA plus 2/3 A wedge A is the Chern-Simons form, and the trace of that is integrated over the three-manifold, and you get an invariant of three manifolds, at least formally, and this has been investigated a lot. And I'm not going into the technicalities of this. I'm just throwing up the slide for the sake of the idea, because for knots, the idea is that the knot is sitting inside this gauge field, inside the three-manifold, and then you can measure holonomy with respect to that. That is, you can move around the knot and watch how the gauge field is affecting that motion and come back to where you started, and you get a linear transformation on the space that you're working with, and you can take the trace of that. That's called the Wilson loop. That part is a well-defined integral and measures how the knot is sitting inside space and the field. But because the field is turned on, it isn't just a function of the knot itself. If you move the knot a little bit, you'll get a change. But the change has to do with the curvature of the field, and so Witten figured out how to integrate something against this and get an invariant of the knot. So Witten's knot invariant looks like this, where you have this exponentiated Chern-Simons Lagrangian, which is sensitive to curvature of the field, and you have these Wilson loops, which are also sensitive to curvature of the field, and it balances out in the integration, but the integration is formal. Nevertheless, one has these invariants, which can be rewritten in other ways, and one can obtain algorithms for doing quantum computations for these things, and I'll explain how one can do that as we go along. So in that sense, we know how to calculate Witten's integral by using quantum computation, but not directly, only rather indirectly. And so the quantum algorithms for color-Jones polynomials, they give rise to quantum algorithms for Witten invariants, and they give rise to quantum algorithms for computing functional integrals, but we don't really know how to do it directly. You could wonder whether there was some way to get at at a quantum model for computing this all by itself in its own language. So that's a problem that's in the back of my mind when I'm thinking about some of these other things that are much easier. That's a bit of background. Here's a slide summarizing some things about topology, and let's talk about topology a little bit. So one has knot diagrams, and this is a very useful way to formulate invariants, and I'll be talking about Jones polynomial in terms of diagrams in a moment. One has the Reidemeister moves, which are available for moving one knot diagram to another, and Reidemeister's good theorem from the 1920s, which tells us that these moves are sufficient for understanding topological problems about knots and links via diagrams. Other things that we have that are very useful to us are braids. One often writes sigma 1, sigma 2, and sigma 3 for the braid generators, sigma n. I've written S's here because sometimes one writes Pauli matrices in this context, and they're written as sigmas. But the braid generators consist of, first of all, braids consist of a number of strands which are always going down and never knotting, but are winding around one another. And if you take a simple braid like this one, 2 twists, you can close it by taking the top strands and attaching them to the bottom strands, and you'll get a knot or a link. So I've illustrated here how the simple braid here gives rise to the simple link of 2 components when you close it. And if you take 3 twists here and then close it, you get the trefoil knot. And if you take 4 twists arranged in this pattern, first sigma 1, then sigma 2 inverse, then sigma 1, then sigma 2 inverse, and close that, you get the figure 8 knot, the next simplest knot. Alexander, also in the 1920s, proved that every knot or link can be written as a closed braid in the sense that I was showing you here. This is one of the nicer theorems of elementary knot theory. You can prove it quite easily. I won't prove it, but I'll describe the proof for you. You have this mess of rope in front of you, and you decide that you would like to turn it into a braid, which means that you would like it to wind around an axis like this, like the braid does, because you see, once you have the braid, you can put an axis perpendicular to the screen right straight through there, and then the braid is winding around that. You're always going around the axis as you move along the braid. And if you were to take a radial cut, you would see the same number of strands all the time as you walk around. So that's what you're looking to do. You're looking to take this mess of rope and choose an axis. You could put a pole through it somewhere, and then you would like it to wind always around the axis. So Alexander's proof is very physical. What you do is you start walking, and if you find yourself going backwards in the wrong direction, then you throw that part of the rope up over the axis or under the axis, whichever is the right thing to do at the time, and keep on going. And by the time you get all the way back to the beginning, it's been turned into a braid around that axis. So that's a description of the proof. I won't do it, but you could try it with a bit of rope and a pointer or a pencil. And it's a very nice proof. Every knot can be written as a braid, every knot or link. Braids have an algebraic structure. The generators are, you have a number of strands, like here we're dealing with 4-stranded braids, 1, 2, 3, 4, and then that's the next braid, 1, 2, 3, 4. So I can twist the first 2 strands, twist the strands 1 and 2, twist strands 2 and 3, or twist strands 3 and 4. I can twist them either to the right or to the left. And then if you multiply in the way I'm indicating, taking the braid and then taking another braid and attaching the bottom of one to the top of the other, then you see that the inverse braids will multiply out to give you something that topologically unwinds and gives you the identity braid. So you see, that's one of the things that happens with braiding, is that there is an inverse to every braid. There's also fundamental relations. This is a fundamental relation in the braid group, S1, S2, S1. And you see it's the Reidemeister move. You can take this arc here and push it down, or you can take that crossing and push it upward a little bit. And you end up over here at S2, S1, S2. So when you express things in terms of braids, you have an algebraic formula that corresponds to the third Reidemeister move. Of course, S1, S1 inverse equals the identity is a version of the second Reidemeister move. And braids are not interested in the first Reidemeister move unless you close them. But as braids, they're not interested. It doesn't happen. Strands do not wind around themselves. So you see that there's one further thing, and that is that if the elementary generators are far enough apart, then they don't have anything topologically to do with one another, and so they commute. So these are the basic relations that happen in the braid group. Si plus 1, Si is equal to Si plus 1, Si plus 1. Sj is equal to Sj Si if I minus j is greater than 2. And so you have generators S1 through Sn minus 1 for the n-strand braid group. And it's a nice algebraic object. It's a group with those generators and relations. And the reason I mention all of this is because a little later on we're going to talk about turning things into quantum processes. That's the idea of quantum computing. And quantum computing is very simple from a mathematical angle at its abstract level where people live when they design algorithms. What they're trying to do is take an algorithm or a mathematical process and write it as a product of unitary matrices. You'll see in more detail. Once you've done that, that's essentially turned your mathematical problem into a quantum process, because a quantum process is a transformation that is unitary. So, if you're trying to solve a problem in topology via quantum computing, then what you need to do is you may need to associate a unitary transformation to each braid. And so one way that you could do that is to associate to every generating braid a unitary transformation. So then you would have, for four-stranded braids, you would have a little lexicon of unitary operators, S1, S2, S3, and their inverses. And then if somebody gave you a more complex braid like this, you could put them together, S1, S2 inverse, S1, S2 inverse, and this would be a unitary operator starting here, ending there, and then you could start to analyze what it did physically and try to understand the model that you're making in terms of the quantum mechanics. So that's what the enterprise looks like, and the fact that you can translate knot theory, which doesn't look at all algebraic at the outset, itself into a certain kind of algebra with braids is really significant for thinking about this kind of thing. Now I want to talk for a few minutes about an invariant. This is a version of the Jones polynomial, and it can be expressed in terms of braids. I don't remember whether I had enough of that in my slides, but as it stands, I'm telling you how to compute it recursively on a knot diagram. And this is a formula for recursively computing this thing. You stand looking at your knot diagram and grab a crossing. And then you transform that crossing in two ways, by cutting it out and replacing it by two parallel lines this way, or cutting it out and replacing it by two parallel lines that way. And then these are smaller knots or links, and you compute the invariance on them. And then you add them up, multiplying by A and A inverse, and you get the invariant corresponding to this. If you switch the crossing to the other kind of crossing, it switches A and A inverse. You might want to remember how to associate the A and the A inverse, and so I've indicated my mnemonic for this. The A's are labeling the regions which are swept by turning the overcrossing line counterclockwise. The A inverses are labeling the regions that are swept by turning the overcrossing line clockwise. When you smooth out the crossing, you cause the two A's to see each other, in which case it gets an A, or you cause two A inverses to see each other, and then you get an A inverse. So that's the formula. Ignore this for a moment. If there's a closed loop with no crossings on it, it gets this value, minus A squared minus A to the minus 2. This turns out to give you a calculation which gives you a polynomial and A inverse, which is invariant under the second and third Reidemeister moves. It needs a little normalization for the first Reidemeister move. And when you normalize it, it's essentially the Jones polynomial. So there's another summary of what I just said using A and B. B is A inverse unless otherwise specified. I'm saying that if you have an extra loop like that, then it multiplies by D. D was minus A squared minus A to the minus 2. Let's look at how it looks in a little more detail. Crossings can be resolved in two ways. You have this recursion formula. When you are trying to calculate, you grab hold of one of the crossings and you smooth it one way, and you also smooth it the other way. You get two things. One might be a knot and the other a link, as in this case. So here, I smoothed it, and I got this link, and I got that knot. Now, it turns out that I know what to do if there are curls. I didn't tell you, but I'll tell you. But when I have a link, I have to keep on working. So I go to a crossing here, this one, and I smooth this the two ways. And in the end, I have these guys down at the bottom of the tree. And all they have are some curls in them. It turns out that I know that when I calculate this, if there's a curl, it will multiply by something. So I can just look at it and say, that's going to be equal to minus a cubed, and this one, and so on. So I can calculate all of these and add them up, and I get the result for the knot. So you see that this invariant is going to be a rather large calculation for the average knot or link. You have to sum over all these splittings. So you will end up at worst with 2 to the n different things to look at. And sometimes you can shortcut like I've done here and have fewer. I got it with 3, but in general, if I used every single crossing and did the algorithm, I would have 2 more here, 2 more here, 2 more there, and I would end up with 8 things altogether. 4 more there, right? 2 crossings there. So that's what the calculations look like. I guess I was missing just a minute. I want to check something. Yeah, all right. Let me just show you that for a moment. You see, if you do the calculation, you will find out that you get minus a to the minus 3 times what was times the curl missing, or minus a cubed times the curl missing when there's a little curl. That's what I was saying. It's easy to calculate that from the rules that I gave you, and that's why when I'm back here, I'm perfectly happy to stop here, here, and here. And so you could continue this exercise if you wanted to and calculate the polynomial for the trefoil knot. I want to talk about how this ends up working, though, for a few minutes. So let's look. If I just had an algorithm of this type, where I expand a crossing and get an A and a B, and the 2 different ways of smoothing it, then I can figure out how it will behave on Reidemeister 2 situations by simply expanding it. And here's the 4 things that you would get if you expanded both of these crossings. You might smooth this one, and it'll give you an A, and you smooth this one, you see it's the opposite crossing, gives you a B. You might smooth this one vertically, which will give you a B, and this one horizontally, which will also give you a B. Or you might smooth this one horizontally and that one vertically, giving you 2 A's. Or lastly, both vertically, giving you a B and an A. And then you see that means that you would multiply by AB times the value of the loop, ABD, and then you would have a horizontal smoothing. Or you would multiply by B squared and a horizontal smoothing. Or you would multiply by A squared and a horizontal smoothing. And the other one is an AB multiplied by the vertical smoothing. Now you want that this would be equal to this. And you can get what you want by making the algebra collapse a little bit. You can collapse the algebra by saying that B will be A inverse. That's what I said before. And that if B is equal to A inverse, then D had better be equal to minus A squared minus A to the minus 2. That's B. And that's where I got the D. And then this is 0. And this is 1, and it's invariant under the second Reidemeister move. So you see there's a little exercise that shows you that you can make it invariant under the second Reidemeister move, and that's where the coefficients came from. And then furthermore, once you've made those choices, you can find out how it will behave under the third Reidemeister move, and you get lucky. Because you see I expand this on this third Reidemeister move situation right there, and it expands into smoothing it this way times an A, and smoothing it that way times an A inverse. But now it's already been set to be invariant under the second Reidemeister move. So I can pull this out and then pull it down under. And this one I just push it along because no calculations are affected by nudging the diagram around by planar isotopies that don't change any crossing structure. So whatever gets calculated from this is the same as what got calculated from that. We don't move the endpoints, and the rest of the diagram is the same. But now you're looking at this, and this is the display of taking it apart in the two smoothing ways from a site that is above this arc. So it's from this. A expanded, you cut it this way and that way. And so this line is a formal proof that the invariant that we are describing is indeed invariant under the third Reidemeister move. Diagrammatic proof of that. So you might have thought the third Reidemeister move would present complexities. It can, but not here. And so this setup is invariant under the two Reidemeister moves, number 2 and number 3. And it behaves in a very simple way under the first Reidemeister move. And then you can normalize it. Here's the way to normalize it, this formula here. You multiply by minus a cubed to an appropriate power, which is set so that whenever this one happens, it'll be multiplied by minus a to the minus 3. And whenever that one happens, it gets multiplied by minus a cubed, so that there's no variance under those curlings, and it ends up being invariant under all three Reidemeister moves. It happens that the original Jones polynomial had a different variable and was defined in a somewhat different way, so the translation to Jones's v is via the normalized invariant and a substitution. That's a fast course in the Jones polynomial, and if you wanted to learn more about it, it's actually a good idea to take these rules and calculate everything about the trefoil that you can, because you will find that because of the fact that A and A inverse interchange when I switch a crossing, that if you switched all the crossings on the trefoil, then the polynomial written in A will flip to the polynomial with A substituting A inverse substituting A. So instead of looking at f of A, you'll look at f of A inverse. The polynomial for the mirror image of the trefoil knot is f of A inverse, if f of A is the polynomial for the trefoil knot. Now, if you found, as you will find, that f of A is not equal to f of A inverse, then you will have proved that the trefoil knot is inequivalent to its mirror image. Because if there was a topological transformation from the trefoil knot to its mirror image by Reidemeister moves, then the polynomials would be the same. We proved that they would have to be the same. So this is capable, this calculation, of checking that the trefoil knot is inequivalent to its mirror image. It is not capable of always checking when a knot is inequivalent to its mirror image. We do not know which knots that are chiral are detected by this invariant. That's an open problem. In fact, we don't know how to characterize all the knots that are chiral, where chiral means inequivalent to its mirror image. It's just not known. Other invariants can see things that this one doesn't, and so on. But this invariant is quite fascinating. And the open problem about this invariant is, the main open problem about this invariant is the following. Does it detect the unknot? So it may be true, but we don't know. You take a knot, put it in front of this invariant, calculate the polynomial f of A. You find that f of A is equal to 1. Does that imply that the knot is unknotted? We don't know. In every case that this has been done with computers, lots of cases, it's turned out that when f of A is equal to 1, the knot is unknotted. But no one knows in general. So that's a little background topology, braids and the Jones polynomial. Let's switch back to quantum theory a little bit. So quantum mechanics in a very tiny nutshell looks like this. A pure state of a physical system corresponds to a unit vector in a complex vector space. I'll come back to why I said pure here. It's the simplest mathematical way of talking about a quantum state. And physical processes applied to pure states take those states to a unitary transformation applied to the state. And you can think finite dimensions here, although if you at one time took a quantum mechanics course, or if you're a practicing physicist and you use quantum mechanics, you may be thinking in terms of infinite dimensional spaces, because you start traditionally in quantum mechanics with Schrödinger's equation, and the space is the Hilbert space of functions that solve the equation. It's infinite dimensional. But for many quantum problems, quantum information problems, one can work with a finite dimensional space of information. So I like to think of this as a unitary matrix, a matrix whose complex conjugate transpose is equal to its inverse. And I'm working in a coordinate space so that if I choose a basis for, I get a coordinate space by choosing some basis for my finite dimensional space. I'm denoting that basis as 1, 2, through n here. And, and so a vector in that space is a sum of complex numbers, coefficients, times the vectors. These vectors are orthonormal. The inner product is given by ket-bra, or bra-ket. I'm sorry, bra-ket. That is a left-pointing arrow thing next to a right-pointing arrow thing is the inner product. So you have that I inner product j is equal to 1. And I inner product j is equal to 1 if I is equal to j and 0 otherwise. And we think of these as corresponding to all of the different measurements that are possible in this idealized experiment. So that means that when you make a measurement, you will get one of these. You won't get the linear combination. The linear combination is happening internally in the description before you make any kind of measurement. So you see a superposition of states before, in the theory. You imagine that there's a superposition of states in reality, but no one knows what that means. But in the theory says I have a superposition of states. That's the information I have. I make a measurement, and one of them happens. That you know. And it happens in this theory with probability equal to the absolute square of the coefficient. And it is assumed that this is a unit vector so that the sum of the absolute squares of the coefficients is 1. Okay? So that means the total probability is 1, as it should be. And the evolution of the state involves the way those complex numbers can add and multiply one another and so on, and is more complex than their absolute values squared. But the frequency with which you expect to get results is given by the absolute squares of the coefficients. So you have measurement-free process, and you have measurements. And they're distinct from one another in the theory. Measurements are quite distinct from the measurement-free process. The measurement-free process is what's described by something like Schrödinger's equation or the Dirac equation. And then the measurement is just what's taken and gets you to start another measurement-free process if you wanted to. It's a curious theory if you're only familiar with classical physics. Okay. And of course, unitary transformations are designed, by their very design, preserve the norm of the vector, the sum of the squares. So the total probability is always remaining the same under these processes, and it's just mixing up the local frequencies. I said pure because in some real problems, you think of it as some statistical mixture of pure states. And for practical purposes and real situations, you need to do that. And the pure state may be just the figment of the theorist's imagination, in fact. But it's a very useful mathematical way to formulate it. A qubit is a vector representing a quantum state in a two-dimensional space whose basis is 0 and 1 for our symbolism. So that means the absolute square of A plus the absolute square of B is equal to 1. You are A and B are complex numbers, so you're looking at a point in the three-dimensional sphere. And if you measure it, you will get 0 with probability absolute A squared, and 1 with probability absolute computing you have a bit, which is either 0 or 1, a unit of information. This is the base unit of information for quantum computing, a qubit. And you see that you only know it probabilistically. You imagine that you have a specific qubit and that you could measure it and that you can carry it around without measuring it, you hope. And then you can imagine measuring it at the appropriate time in your thought experiment. Here's an example. Well, let's see how we're doing in terms of time. Okay, here's an example. This is a Mach-Zehnder interferometer. It's made out of two types of mirrors, a transmitting and reflecting mirror, 2 copies, and an ordinary reflecting mirror here. And I'm going to make the action of each of the mirrors quantum. We get qubits to come in, and if a 0 comes in, it will be reflected to be a 1 or transmitted to be a 0. If a 1 comes in, it will be reflected to be a 0 and transmitted to be a -1, change of phase. Now, what does it mean, it will be? It means that the output of the mirror is the linear superposition of 1 and 0, equal probability. So that means that H, the half-silvered mirror, applied to 0 is equal to 1 plus 0 divided by the square root of 2. It's equal to 0 plus 1 divided by the square root of 2. And H applied to 1 is 0 minus 1 divided by the square root of 2. So the formulation looks like trajectories that could go out from the mirror one way or the other. And you can think that way if you like. But from the point of view of quantum process, as we've described it, it's this unitary transformation. And what comes out of the mirror is the superposition of these, unless you were to measure. And if you measure right then and there, you're going to see one or the other and not both. Okay? And the other mirror switches 1 to 0 and 0 to 1. And it's given by 0, 1, 1, 0, like that. Then this entire process is first do H, then do M, and then do H. And if you multiply these matrices out, they're both unitary. If you multiply them out, you get 1 minus 1, which means that if a 0 goes in, it comes out as a 0. And if a 1 goes in, it comes out as a -1 with a phase change. If you look at it from the point of view of trajectories, you will get the same story if you look at all the possible trajectories through the system and add them up at the end. I've drawn it here, and you might believe me and believe that when these got added up, you got a 0, meaning that nothing came out here when the 0 came in, but a reinforced 0 came out here, and that's what this is telling you about 0 going into the system. So this is an example of the path integral formulation of quantum mechanics. Elementary quantum processes can be thought of as branching path prescriptions, and then when you concatenate the processes, you will get multiple branching paths, and you add up over all the paths the products of corresponding things, and you get the amplitude for the result, and you follow the rules that I just told you. But that is the rule for matrix multiplication, adding up over all the paths and the products. So it's exactly the same at the finite dimensional matrix level as multiplying the processes composing the unitary transformations. So that's a little example that's worth thinking about in relation to how quantum mechanics works. I'm going to show you a couple of quantum algorithms. This one is useful for doing topology, as we'll see later on. What it does is it's a quantum algorithm for computing the trace of a unitary matrix. So here's an arbitrary unitary matrix, and I'm looking at it as a black box. I can't look inside and see the diagonal elements and get the trace. I can't do that. It's been made into a physical process, and all I can do with it is measure what happens if I give it an input and see what happens in the output. That's all I can do. And I want to get the trace of the matrix. So that means I would like to get entries of the form phi. I forgot what Greek letter I was using. I want to get entries of the form phi u phi. I want to find out what they are for a given phi. So I make this apparatus. I take the unitary matrix, which is already an apparatus, and I make a little extra thing which controls it. And in this control, if a qubit is coming along here and it's a 0, then this will be shut off. But if a qubit is a 1 coming along in here, then this will be turned on and it will operate. So this is a controlled U. I make a controlled U. I have an extra line here, an extra tensor line, and my input is 0 tensor phi, and then the 0 is turned into an equal mixture of 1 and 0 by the Hadamard. Hadamard applied to 0 is 0 plus 1 divided by the square root of 2. So I get an equal mixture, which means that with equal probability, this will be operating and not operating. Phi is coming in here. Then for technical reasons, I have a Hadamard coming out of this line. And then I measure the total output, which is some vector involving the tensor products of those. I measure and ask, what's the frequency of 0? With what frequency do I get a measurement where I get 0 tensor something? Because what will come out will be 0 tensor something plus 1 tensor something. And every time I measure, I will get either 0 tensor something or 1 tensor something. With what frequency do I get a 0 coming out? And the answer, if you do the calculation, according to the rules we talked about, is 1/2 plus the real part of what we want divided by 2. That means that a multiplicity of observations on this system, continuing to make the initial state again and again, will get closer and closer to the real part, will let me get closer and closer to the real part of that diagonal entry in the matrix. You can use a little probability theory to figure out if you have an error bound. You can use Hofting's inequality, for example, and figure out an error bound for knowing how close you are to the answer. But it's a statistical matter. And you only got the real part. But by doing it again with a little phase shifter in here, you can get the imaginary part in the same way. And that's a good example of a quantum algorithm. That's what they look like. A certain unitary transformation constructed for mathematical purposes to let you figure out the statistics of something, and you worked out beforehand that the statistics of that contains the right information if you only knew the statistics. So it looks like a hard job, but in some cases, computers of this kind are theoretically better than their classical counterparts. Here are a couple of examples. This is Grover's algorithm. Grover's algorithm wants to find a particular entry in a list. So you make a vector, so in the algorithm, you make a vector space consisting of the possible entries in the list. That's the basis. That's the orthonormal basis. And then you make up a state vector which consists of the sum over all the elements in the basis. So that's just the list itself in equal version of the list. Then you have the vector that corresponds to what you're searching for. And now the idea is to use unitary operations to rotate this to get it closer to that. And Grover's idea was quite geometric. He used reflections in planes perpendicular to W to rotate S a little closer, and then figured out an optimal number of rotations to make to get it as close as he could to W, and then you can take the inner product, or you can measure. What I mean is that when you measure S, you will have a higher probability then of getting W than you did before, because it will have a larger component. It started out with equal components, and it ends up with a larger component. So that's Grover's algorithm. Then another very important algorithm from the point of view of the history of this subject is Peter Shor's prime factorization algorithm. If you're interested, you can find his original paper on the computer list, on the archive. It was published in '96, and so one of the earlier papers on the archive. So if you look up Peter Shor, you can find this paper. And Shor's algorithm is a quantum algorithm for factoring numbers, and it's better in principle than known classical algorithm of Shor's algorithm. And they explain to you nicely the basic idea in using Shor's algorithm, which is based on finding the period of a certain number theoretic function. That's what the quantum algorithm is doing. So now let's talk more generally about gates and quantum algorithms. Let me skip this forward from this slide. Here is an example of a quantum gate that corresponds to NOT. It's operating on a 2-qubit space, and just like the controlled unitary that I had before, this is a controlled knot. If you have a 0 in the first qubit, it's just the identity. But if you have a 1 in the first qubit, it changes a 0 to a 1 and a 1 to 0. That's its matrix, right? And that's a unitary matrix. So there's a controlled knot. And that's useful because you would think, if you were trying to design computers like this, that maybe you could get away with what happens with classical computing. In classical computing, really all you need is a knot, and you need to make and or, and a couple of simple logic operations, and then you can build circuits and go ahead and you can make anything you want, right? Computation is really very simple at its binary base. Well, what happens at the qubit base? Well, in the qubit base, you need something like the controlled knot. You need a 2-qubit gate. We'll say that this gate is universal for quantum computation if it, together with certain local unitary operations from the qubit space to itself, can generate all unitary transformations of a complex vector space up to density, getting as close as you like. All right? And it turns out that the C naught, together with these explicit 2x2 unitary gates, well, these are just operating on single qubits, rotating them, are enough. All right? If you want to be more relaxed, you can just say, I will take all U of 2 transformations altogether. But you don't have to. You can take a certain special subset of them, plus the C naught, and that's enough to build any quantum computer in principle. With that in mind, you can then ask, well, could I maybe use something other than C naught? Maybe there are other two qubit gates that would be good. Maybe some of them could be topological. And there's a theorem due to the Berlinskys, which gives a general criterion for G to be universal, and that is the following, that a 2-qubit gate is universal if and only if it's entangling. Entangling is a very interesting concept. What it means algebraically is this, that G applied to some single pair of qubit, like 0, 1 or 1, 1 or 0, 1, is not decomposable as a tensor product of 2 qubits. So you take something which is a tensor product, like that, and you apply G to it, and you get something which is not decomposable as a tensor product, then we say that the image is entangled, and what you need is that G should be able to entangle somebody. If G can entangle somebody, then it's good enough. So you can use any G whatsoever as long as it will entangle somebody. You can check as an exercise that C naught can entangle some states. Here's an example of an entangled state and a story about it. This state here, 0, 1 plus 1, 0. You cannot write that as a product, as a tensor product of 2 one-dimensional states. It's not possible. You can check that. And this is often used as an example of a description of non-locality, where this state is supposed to be describing something which has been separated. You started with 2 particles that were nearby one another, one in the star condition and the other in the sharp condition, whatever that is, and they move apart so that one of them is in New York and the other is in San Francisco. But it's still one quantum state. And so at its mathematical level, it's described by this. And if you measure it, you will either get 0, 1 or you'll get 1, 0. You won't get both. You only get 1. And when you get 0, 1, that means that over in New York there was a 1. And when you get 1, 0, you know that over in New York there was a 0. If you got 0, 1 by making the measurement in California, you would know you got a 0, and you would know, therefore, that the person in New York, if he looked, would get a 1, and vice versa. So that the information is spanned across a geometrical distance, according to this theory. So that's called the EPR state. Einstein, Podolsky, and Rosen, who wrote a paper being skeptical about this possibility. So you can check easily enough that if you have a 2-qubit pure state, with coefficients A, B, C, and D, then this looks like a matrix, right? 0, 0, 0, 1, 1, 0, 1, 1, and the determinant of that matrix, non-zero, is equivalent to it being entangled, not being a tensor product. So if you're working with 2-qubit states, entanglement means a certain determinant is non-zero. Another famous set of entangled states are the Bell states here that I've written, and a matrix R. This matrix, it turns out, is very entangling because every image of 0, 0, 1, so on, each of these is entangled. And this matrix, therefore, could be used for universal quantum computing. But this matrix turns out to solve the Yang-Baxter equation. It solves the braiding equation. So it's topological. It's a natural equation, a matrix that occurs in quantum information theory, and it also solves the braiding equation in the following sense. I think of these lines as being the tensor lines for the qubits. So this is a V, and here's another V, and here's another V. So this is acting on, our tensor 1 is acting on V tensor V, 2-qubit gate, tensor 1 more. And then what you see if we divide it up braid-wise is R tensor the identity tensor R, and R tensor the identity when you run this one. When you run this one, you see the identity tensor R tensor the identity, and the identity tensor R. And if you did the matrix computation for R, you would see that this equation is true. So that means that R partakes of a relationship with topology. It has the same pattern as the third Rademeister move, or the braiding relation. It means that if you were to draw circuit diagrams for quantum computers, and in your circuit diagrams you had these looking like this, you could replace them that way topologically. It would be a topological quantum computer if it was entirely a braid. But it isn't necessarily entirely a braid. Remember, you also need those local unitaries. The local unitaries are little matrices festooned on the single lines, and they can get in the way of this kind of invariance. So I would call a computer that was built on the basis of the Bell basis matrix R and the local unitaries a partial topological computer. The reason for looking for topological quantum computers is that they might be based on processes which are topological, in the sense that if you perturb the process a little bit, it will still have the same quantum result. That's the hope, you see. And some processes look like they could do that, but they may be very hard to implement. That would make the computer resistant to perturbation. And the problem with designing quantum computers in reality is always perturbation. We're talking about pure states here, but pure states don't quite happen. You could try to approximate things that are pure, but what happens is you have a complex environment, and as soon as time goes on and processes go on, the states start getting perturbed. They decohere, as the term goes, and the information will get lost into the miasma and chaos of all those interactions. So if you have something which is topologically invariant to perturbation, that could be good. And so that's one of the hopes for using topology in quantum computing. So I just said this. Certain braiding operators are universal quantum gates. This is the Bell matrix. Here are some other examples that work. Some of them are, this one, curiously, is related to the Humfley polynomial, another non-invariant, but I won't go into that. So there are some issues here. Giving a universal gate that is topological gives partial topological quantum computing, as I said. And nevertheless, these Yang-Baxter gates are interesting to construct and use to think about other things as well, like the relationship between topological entanglement, linking, knotting, and quantum entanglement, which is what we were just talking about. Then there's another matter, which I want to discuss for a few minutes. I see that we're going to have to stop soon. I won't do everything I had intended, but that's all right. Here's a topic that's a little more recent. Partial topological quantum computing via Majorana fermions, so-called, is a possibility. A Majorana fermion is a fermion, like an electron, that is its own antiparticle. Electrons are not their own antiparticles. Positron, electron, they're different. A Majorana devised the idea of thinking about particles that could be their own antiparticles a long time ago, and thought possibly the neutrino was a particle of that type, but no one knows that either. However, mathematically, an electron or any other fermion's creation and annihilation operators are combinations of Majorana fermion operators, which are quite simple. The two operators that would correspond to creation and annihilation for a fermion, for an electron, can be written in the form A plus IB and A minus IB, complex conjugate. Annihilation, creation. And then these have products that you can figure out. But the algebra for the A's and the B's is very simple. It's just that AB anti-commutes, so you have AB equals minus BA, and that A squared and B squared equal 1. All right? That's the algebraic structure for the Majorana fermions. And a row of n electrons can be thought of as a row of 2n Majorana fermions mathematically. And recent work suggests that Majorana fermions can be detected in nanowires. And I'll give you a little bit of a view of that. But I want to do a little algebra first. So suppose you had 3 Majorana fermions, A, B, and C. They square to 1 and they anti-commute. Then here's a little bit of lore that I think you'll like. You let I be equal to BA, J be equal to CB, and K be equal to AC. And then you can do in your head that I squared, J squared, K squared, and IJK equal minus 1. So you get the quaternions. This is just an abstract transformation that takes you from this simple Clifford algebra, A squared equals 1, B squared equals 1, C squared equals 1, into the quaternions. And then if you were to take these guys, 1 plus I, 1 plus J, 1 plus K, appropriately normalized, you will find that every pair braids, ABA equals BAB, and so on. So you got a little triangle of braiding there. And so the braid group is actually deep in physics. It's right there at the bottom of beneath the electron in its mathematical structure. This is kind of exciting, but very elementary. And I'll come back to it in a moment. But here's a bit of thing you could look up. Evidence for Majorana fermions in nanowires. There's an article in Physics Today last year. And here's what some of that looks like if you were to look at one of the papers. Thinking of a row of electrons, but then maybe these are the electrons, but then some pairing occurs between the electrons, and you end up with the Majorana fermions sort of end out. I think the next slide is better for that. There. Right. So you see electron, 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 but then this binding occurring between the neighboring electrons, leaving out at the ends Majorana fermions. That would be the theorists looking at this and saying that could happen. And then these guys might be correlated to one another, and maybe we could measure that, and we could do this. And then they actually did some experiments with superconducting, very thin wire and superconductors and so on. And these people in Holland claim to have detected what you would expect to happen if there really were Majorana fermions in that wire. So that's one side of things. That's a very interesting experiment, and I don't know much about it. And then there's this braiding phenomenon that I was just telling you about. If you take a row of Majorana fermions instead of just 3 and define those same operators, 1 plus AI plus 1 AI, and you'll find this is the inverse, then you will get a representation of the Art and braid group. The ones that are far apart will commute. You have a braid group representation. They're unitary, and they act on the individual Majorana fermions by interchanging them in pairs with a change of sign, like that. You can think about this geometrically. Here's this row of Majorana fermions. You take one pair of them and interchange them, and then by this representation, it's just like an old piece of the belt trick where, well, I'll just use the slide, where you have a belt and it's untwisted, but we interchange the two ends of the belt. And interchanging the two ends of the belt makes it twisted, right? That's the braiding. And then you have a 360-degree twist on that belt. Then in this algebra, the 360-degree twist is associated with the left one. By some magic, quantum computers, by using nanowires and Majorana fermions, maybe. There are other schemes which are also very difficult to imagine involving other physical effects. There's an effect called the quantum Hall effect where you have a plate which is super cool, which is very cold, and you have current running through the plate this way, a specific potential, and then you watch how the resistance of the plate transverse to that potential in a magnetic field behaves in a quantized way. People theorize that what happens in that plate is that collectivities of electrons form vortices, and these vortices can braid around one another, and you could try to do topological quantum computing with them. I think that this is a good place to stop, although the story goes on. And I just told you a little bit about the other part, the part about the quantum Hall effect and the other braiding, which ends up being related to the Jones polynomial and braid group representations that are related to the Jones polynomial. In that other version, one gets full-bore quantum computing, but the actualization of it looks far away. I mean, you really get representations of the braid group that represent the local unitaries as well as everything else in the part that's related to the Jones polynomial. So that's a very interesting story, but we don't have time to do it today, and I'll stop here.